Have left, we will spend in review. Okay? So we're only going to do the main notes. We're not going to do that any supplemental stuff that I put in here. All right? So your 1.4 notes look like this. It says at the top, notes, topic 1.4. Okay, that's what we're doing. This is stuff, I think you're going to think this is really easy. I hope you do anyhow. I want to get started here. At the very beginning of the year, Mrs. Ford said you need a binder because you're going to have a ton of paper. Some of you didn't listen to me. We need to get ourselves organized. All right, here we go. Polynomial function, there it is. There's the definition of a polynomial. I'm not writing that on the board, it's big and ugly. N is a positive integer. A sub I is a real number for each I from 1 to n. And A sub n is non-zero. So, look at that polynomial. What is the leading term? What do you think the leading term is of the polynomial? A sub n x to the n. So, like, you might have a polynomial that's 3x to the 7th. That would be the leading term. What is the degree of the polynomial? This is the leading term. What's the degree of the polynomial? N. N is the degree of the polynomial. So in my example, 3x to the 7th, the degree would be 7. And then what is the leading coefficient? The leading coefficient is A sub n. Whatever that is right there, that's the leading coefficient. Now, the reason that he has highlighted in his notes here, I think he's from Mr. Passwater, the reason he's highlighted that is because as we get ready to sketch polynomials, that number, particularly the sign of that number, positive or negative, and the degree of the polynomial, those two things tell us basically what the shape of the thing is going to be. Okay, those are important numbers. All right, find the leading coefficient and degree of these functions. So for problem A, what is the leading coefficient? 3. And what is the degree? 4. Done. Easy, easy, easy. Everybody got it? All right, now B, he tried to trick you. What is the leading coefficient? Negative 7. The polynomial must be in what we call descending order, which means the powers go down. So the first term is negative 7 x to the 3rd. So the leading coefficient is negative 7, and the degree is 3. Ooh. Ooh. Ooh, what about this guy? Could we write this like this? Yeah. So clearly, what's the degree of this polynomial? 0. The degree is 0. What's it look like when you graph it? It's a horizontal line, so it's not very interesting. You could probably say your leading coefficient is 4, but nobody ever does because constant functions just aren't interesting. But it is 4x to the 0. So you could say the leading coefficient is 4 and the degree is 0 for a constant function. Okay, the extrema are the minimums and maximums of a function. There are 2 types of extrema. There are what we call relative or local. Those 2 words are interchangeable. Relative and local are the same. And then there are absolute and global. Those 2 are the same. Okay? So you can have relative or you can have absolute extrema. Take a look at the picture, that first picture there. It says, where is the local minimum? There is only one local minimum, and it is where x equals 0. Would you agree with that? A local minimum is the bottom of a valley. A local maximum is the top of a hill. So there is one local minimum, and it's where x is 0. There are two local maximums where x is -2 or 3. Same picture. Absolute maximum. Now the absolute maximum is the very highest point of the graph. So where does that happen? It's where the maximum is 2 at x equals 3. So the value of the maximum is 2. Would you agree with that? 2 is the highest point. And it happens where x is 3. Now what about an absolute minimum? There isn't one. Why not? Because the curve goes down forever and ever. So we just say there is no absolute minimum in this problem. Okay? Easy, easy, easy. All right, example 2. Here we go. Got a new picture. Got a little parabola. Relative minimum where? Does this picture have a relative minimum? No, it does not. There is no valley in the picture. So therefore, there's no relative minimum. How about a relative maximum? Yeah, it's where x equals 1. Yeah. How about an absolute minimum? Doesn't have one. Guys, it goes on for, see those arrows? Those arrows are important. Goes on forever and ever. No minimum for a parabola that opens down. However, there is an absolute maximum, and it is 3. The value is 3, and it happens at x equals 1. That point, 1, 3, is called the vertex of the parabola. That's a very important point. It's also the maximum. All right, B, question B. Take a minute, see if you can fill in the blanks there for the curve in question B. I'm looking at example 2B. Do I have a relative minimum in this picture? Yes, because I have the bottom of a valley. So where does that happen? It happens where x equals -2. Do I have a relative maximum? Yes, I do, because I have the top of a hill. So that happens where x equals 3. Do I have an absolute minimum? No, because if you notice, there's an arrow on the one side of the picture, and it's going down, so there's no minimum. It just keeps going, right? So no absolute minimum. Is there, however, an absolute maximum? Yes, because the other side of the picture doesn't have an arrow. Did you catch that? So the highest point in the picture is the maximum is at 2, or is 2, maximum value is 2, and it happens where x equals 3. Good? All right, do C, take a minute with C, see if you can figure that out. Got a little tricky thing there. Talk about it. Did you find a relative minimum?
Yeah.
Actually, did you find 2 of them?
Yes.
Okay, so your relative minimums happen where x is -3 and 3, x equals 3. Now here's where it gets tricky. Relative maximum, there are actually 3 of them. You wouldn't realize that because I told you they were tops of hills. So hopefully you got one at 0, relative maximum at 0. But there's also a relative maximum at -4 because relative to the points around it, isn't that the highest one? And that's what a relative maximum is. Relative to the points around it, it's the highest. So x equals -4 has a relative maximum.
Would that be the same for B then, since there's an endpoint right there?
For where now?
For question B,
For B?
X equals
Yeah, we could say that's a relative maximum also. Yep, I missed that. So -4, thank you. And then, look at the other side of the picture, I'm back on C now. Isn't there a relative maximum at 5? Yeah. Is there an absolute minimum in problem C? Yes, and it happens at the point -3, so the value is -3, and it happens when x is -3. And is there an absolute maximum? Yes, and it happens, the value is 4, and it happens when x equals 5. Everybody good with that? All right, fun facts about polynomials. Between 2 real zeros of a polynomial. Now, I want you to remember, real zeros are like x-intercepts. So between 2 real zeros of a polynomial, there must be at least what? At least one what? Think about, you have to connect these 2 dots. Never with a straight line. Not in polynomial land, everything is curvy. So when I connect these 2 dots, don't they have to be connected like that? Or like that? So between any 2 real zeros, there is at least one relative maximum or relative minimum. Now, there could be more, because certainly the picture could do, funky stuff. But there has to be at least one. Does that make sense to everybody? Polynomials of something degree, that would be either even or odd, must have either a blank or a blank. Now, I want you to think about, we haven't gotten to much of this conversation yet, but an even degree polynomial would be like x squared. And x squared looks like a parabola. Okay, so let's just think about x squared parabolas, even degree. Every time I draw one of those, put a negative in front of it and it looks like this, right? Every time I draw one of those, what do I have to have? A vertex, which is either going to be a global maximum or minimum, depending on which way the curve is opening. So polynomials of even degree must have either a global max or a global min. And remember, instead of global, you could be using the word absolute. They mean the same thing. All right. Do this next page, and we'll be done, and we can start reviewing some of that. We're gonna get this page done. A point of inflection occurs, we talked about this already, when a function changes from concave up to concave down, or vice versa. At a point of inflection, the rate of change of the function changes from increasing to decreasing, or from decreasing to increasing. Okay, that makes sense because the concavity is changing, so the rate of change is changing. All right, look at example 3. Use the graph to find any values where the function has a point of inflection. All right, take a minute to look at it. This one's pretty easy. They're not always so clear, but I think this one's pretty clear. When does it look like, or where does it look like I'm changing from concave up to being concave down to going back to concave up? Where does it look like that change is happening?
-1.
At -1. I'm looking at x values. So where x is -1, aren't I, doesn't it look like I'm changing there? And then where's the other place at x equals 1? Now, if somebody, I mean, those are like the easiest numbers to look at, but if somebody wants to argue and say, oh, I think it's -1 1/8, okay, it might be, but it's somewhere around -1 and somewhere again around 1. That's where your concavity is changing. When you take calculus, you will learn how to find those points right on, exactly. Right now, we're just eyeballing. All right, for each of the following intervals, determine if the rate of change is increasing or decreasing. Explain your reasoning using the graph. This explain your reasoning is what some of you are struggling in your homework. You've got to have a reason for the answer you put down. So go ahead and do those. Do those intervals. You're going to say whether it's increasing or decreasing, and then you're going to tell me why. Looks like we are all here today. Now remember, you are not answering this question about the curve itself. Okay, so if you're using words like it's going up or something, no, that's not right. We're not talking about the curve itself. We're talking about the rate of change, which has to do with the concavity. That's your rate of change of the slope. That's your concavity. So from 3 to 4, would you say it's increasing or decreasing? Increasing. Why? Because there's a positive rate of change, but it is concave up. The answer, the explanation you need to get in the habit of using refers to concavity. Concavity tells you if your rate of change is increasing or decreasing. If you are concave up, your rate of change is increasing. Okay? So how about the next one? -4 to -3. -4, now be careful. -4 to -3, the curve itself is decreasing, but we're talking about the rate of change. Increasing, because that is concave up, guys. Concave up means the rate of change is increasing. The curve itself is decreasing. So that would be one of those questions that says, where is the curve decreasing, but the rate of change is increasing? That would be right there, concave up. All right, what about -1 to 1? Oh, -1 to 1, decreasing because that whole chunk is concave down, right? And what about 1 to 2? Increasing because it is concave up. I know it's confusing, but you really have to read the question carefully. the rate of change between 1 and 2 is increasing because the curve is concave up. The curve itself is decreasing because the slope is negative. Got it? All right, get out your handy dandy calculators. And one more problem. When you get to calculus, you will be able to do this problem without a calculator. But right now, our only hope is to use our calculator. So negative 1.37x to the fifth plus 4.218x to the fourth minus 0.357. Make sure I'm copying this right. I want to make sure I'm getting that right. Okay, so I'm going to put in that equation into my calculator. Everybody know how to put that in? Everybody know how to get x to the fifth? Use your little caret button. That little guy right there. Before you hit graph, or maybe it's too late, maybe you already did, I want you to pay attention to how your windows should be set. Did you notice what's the very first thing they tell you in this problem? For t or x, where? 0 to 3. So when you set your window, x min is 0, x max is 3. Now it doesn't really tell me anything about my y's, so I'm just going to, they're at negative 10 to 10, I'm just going to leave that and see what happens. I think I'm going to make my y a little bit bigger. I'm not sure what's going on up there. I might go to 100. Yeah. I would say, I would change your y max. I went to 100, I would change it to at least 50. And you should see something that looks like this. Is that what yours looks like? Something like that? Now, I want you to read the question. Where's my question? At what time does the number of cars in the parking lot change from increasing to decreasing? Now, think about that for a minute. What are we talking about? What point are we talking about in this picture? If we want to go from increasing to decreasing, aren't we talking about that point? So we'll find that the same way we find everything else. We'll do second calc maximum. We'll set our left bound over here somewhere. Our right bound over here somewhere. And then we'll go in between them for our guess, somewhere between those bounds. And did you get 2.446, 31.898? So now we need to answer the question. Using this model, at what time t does the number of cars in the parking lot change? Well, about 2.5 hours. I'm not sure how to answer this reasonably. T is 2.446, but if I were thinking about this, about 2.5 hours after I started measuring, I don't know what 0 is. What does this number represent? That's the number of cars. So the maximum number of cars in the parking lot is 31. maximum I can fit, or the maximum people that park in that lot. You okay with that? Everybody okay? All right. Your 1.4 homework is going to be due on Monday. Actually, you know what? I'm gonna make it due on Tuesday. Because we're gonna have a quiz on Monday and I want your energy to be focused there. Okay? So that's it. For 1.4, we're done with it. Let's do the homework, turn that in. They do the homework today. We're gonna turn that in by Tuesday, before Tuesday, by Tuesday. Now, get out the other two papers you picked up today. And we're gonna get these done. We only have 8 problems on the first and 4 problems on the second, so we should be able to get this done. Alright, so we're gonna have a quiz on Monday. Basically over everything we talked about in chapter 1 and so far. Okay? So, here we go. First one we're gonna look at is the one that's stapled, the little stapled one, called Two Truths and a Lie. So, you're gonna look at each problem, and 2 of the statements are true. 1 of them is false. You need to explain why it's false or correct it so it's true. Alright, go.
First one's true. Yeah, it's got my stomach yeah, it's pretty.
Yeah.
Yeah, I was
Okay, we're gonna do all 8 of these guys, so let's figure out what's happening there. Anybody who turned in homework today, I will have that graded and you can pick up tomorrow if you care to see it before you take the quiz. You can swing by tomorrow and pick it up.
Yeah, I'm doing everything in my power to
So guys, are we moving along okay? Andy, you finished?
Oh, yeah.
Oh, yeah.
I was glad to do these.
All right, let's start talking about these. Some of you may not be quite finished, and that's okay. Let's talk about them. So, follow the directions. Identify which statement is false, explain why it's false, or correct it. So, Sander, you got number one, since you were done.
Yeah.
Yeah.
So, I said S3 was the one that is false because, it's concave up instead of concave down.
There you go. That's it. That's it. That statement is false because the curve is concave up. So if you change the down to an up, you corrected the statement. Would everybody agree? Easy? Okay. Who's got two for us? Who's got two? Okay, Mr. Ron?
I said that S3 was false because, it's concave up on the angle.
That's like another, the same problem, right? Isn't it the same thing? Everybody good with that? Concave up. All right, who's got three? Okay, Kennedy?
I said S3 was false because it was a change in concavity at X.
Exactly. So if you wanted to keep it concave up, you would have to make it like from 1 to 3 instead of -1 to 3. But you explained why it's false. There's a change in concavity. What do we have there? We have a point of inflection. Yeah. Okay, good. So far, the third one's always false. Okay, what about problem 4? Who's got that one? Raina?
I said S2 was false because it's increasing from 5 to 6, but decreasing 6 to 7.
Exactly. So if you wanted to say it was increasing and concave down, that would be just from 5 to 6 maybe? Would you agree with that? Okay. All right, who's got 5? Okay,
I said S2 because at X equals 3 is open dot.
Okay, yes, there's an open dot there, but we have what we call a discontinuous function. We have to lift our pencil. But did you notice that there is a closed dot at 3? So K of 3 actually has a value. What is the value at K of 3? -2. So it is not a 0. This says it has a 0 at X equals 3. No, it doesn't. It has a Y value of -2 at X equals 3. A 0 is an X intercept. So that statement is false, absolutely. Here's how you correct it. K of 3 is -2. All right, how about 6? Anybody think you have 6? Bob? Ellen?
Oh,
Share.
for number 6?
Yeah.
I said false for S3.
It's okay. Why did you say that?
Because when it's concave down, it has to be decreasing for the Y.
Okay. Okay, so let's look. This says when X is less than 0. Okay? So Ellen, I want you to look at everything to the left of the Y-axis. Okay? So it says that it's increasing and concave down on the whole left side of the y-axis. Now, I would agree that it is increasing on the whole left side. Isn't my pencil going up? Isn't the slope positive all the way up? But it isn't concave down on the whole thing. It's concave down until we get to -2, and then it becomes concave up. So, concavity changes, like Kennedy used this terminology earlier, concavity changes at -2, or there's a point of inflection at -2, and the curve becomes concave up. All right? Very good, Ellen. Super. All right, who's got 7? Anybody have 7? Josie, you got a thought on 7?
I didn't get that far.
Didn't get that far. That's okay, yeah, because I kind of rushed you a little bit. Who, did anybody, Patrick, we know you did. What do you have for number 7?
I said it was S1 was the false one.
Okay, so let's look at that statement. That's statement number 1, and it says the curve, or the graph of m of x is increasing when m of x equals 0. Okay, now when we say m of x equals 0, that means y equals 0. So I want you to look on the curve where x is -2 and where x is 5. Those are the 2 zeros, okay? And at those 2 points, isn't the curve increasing? We're talking about the curve itself. We're not talking about the rate of change. We're talking about the curve itself. Positive slope, going up. I think that's a true statement, Patrick. I think S1 is true.
I think it's S3.
S3 is false, Kennedy says. What's false about that one?
When y is greater than 0, it's increasing.
When y is greater than 0, it is increasing for part of it, but it isn't always increasing, is it?
No.
Comes back down at -1, right? So between -1 and 1, the curve is decreasing?
That's a change in rate of change.
Yes, yeah. Okay. Okay. And finally, number 8. Who got that one? Anybody got that one? Number 8? Mr. Funk, what'd you think?
Well, I didn't get to the back page.
Okay, that's all right. That's okay. Pay attention now because we're going through it. Emily, did you get number 8?
Yeah, I put S3 was false.
S3 was false. The graph of the curve is positive on the interval from -2 to 6. I think that's true. Now, it isn't talking about it's not talking about increasing or decreasing. It's talking about having positive values. So d of x, that's y, is y positive between -2 and 6? It is. That's a true statement. That's a true statement. Anybody know the false one in number 8? S1 is false, because the curve is not concave down between -2 and 6. There's a point of inflection somewhere in there, like around 2. So the concavity changes inside that interval around x equals 2. Got it? Okay, last thing we're gonna do then is this 4 corners thing, and we're not gonna play any games or anything, we're just gonna do the problem. So, what I have up here are the first 3, because they all involve average rate of change. I haven't even looked at the pictures, looked at the equations, looked at the charts, haven't looked at anything. If I'm doing average rate of change from -2 to 3 on that interval, it's the y value at 3 minus the y value at -2 over 3 minus negative 2. Are you clear on that? That is huge. I did it here. My interval is negative 3 to 9. So it's the y value at 9, f of 9, y value at negative 3 over 9 minus negative 3. And the same thing here. All right? Calculate those. You have to be able to find your y values. You have to be able to find these using an equation, using a graph, and using a chart. So see if you can do that. Real quick, find those rates of change. These are going to be just numbers. We're going to get a fraction. Now, kids always say, Miss Ford, I know I need to plug 3 in for X. Where do I plug it in? Well, pay attention to this. Where does 3 fall? Is 3 less than or equal to 1? No, 3 is bigger than 1. So where do you plug it in? You plug it into this one. So f of 3 is going to be 10. All right, now where are you going to put in your f of negative 2? Well, isn't that going to go in here? Right? Because negative 2 is less than 1. This tells you which x's to use. So what do I get when I plug in negative 2 there? Negative 8? 18 over 5. Done, done, done. If this were a word problem, you'd put a unit on that, like feet per minute, or whatever. But it's not, it's just numbers, so that's our answer. We can talk about this some more. Who needs further explanation for this? Does everybody know where these numbers came from right here? Quinn, you know where they came from?
Not really.
Okay, right here. This is my x value. Is 3 bigger than 1? So I put 3 in right here.
Okay.
Is negative 2 less than 1? So it gets plugged in here. I could have plugged negative 2 in this one because it's not greater than 1. All right. Now, look at the next one. Now this was an equation of a piecewise function. This is a picture of a piecewise function. Find where x is 9. What is the y value when x is 9? 3. 3. Look at your picture, guys. If x is 9, isn't y 3? So f of 9 is 3. This is a y value. All right, what about negative 3? What is the y value at negative 3? Negative 2. And then over 12. Did you get 5 over 12?
Yeah.
You're right. 5 over 12. Average rate of change. Y minus y over x minus x. Okay, for the last one there, number 3, you have a chart. What's f of 7? If t is 7, then what's f of 7? Negative 4. What's f of 2? 3 over 5. Did you get negative 7 over 5? Okay, we got it, folks? We got those 3 figured out? Average rate of change using an equation, using a picture, using a table. Okay. Verbal. Let k be a continuous linear function with an average rate of change, aka slope, of negative 3. It has a y-intercept of 5. You guys, negative 3x plus plus 5, I probably shouldn't use y, I'm using k of x. Yeah, there's words, but you know all those words. You know that. So now it says, what is the x-intercept? No. When y is 0. So you are going to solve this equation. The x-intercept has a y-coordinate of 0, right? So where is it? X is 5/3. 5/3. Okay? All right, we have 6 minutes. So here's what we're going to do in 6 minutes. You are going to do whatever preparation you need to do. You go get your phones. You have 6 minutes to do whatever you need to do. I'm going to sit right here and wait for you to come to me with questions. We have a quiz on